Good afternoon, everyone. Thank you for joining us today for Koch Modular's webinar around liquid-to-liquid extraction titled Understanding When and How to Apply Liquid-to-Liquid Extraction to a Separation Problem. My name is Mauricio Villegas. I am Koch Modular's Business Development Manager here in Houston. And again, thank you for joining us today. A little bit of logistics for today. We'll be answering some questions. We've allotted about 5 to 10 minutes at the end of the webinar for questions. So please feel free to post your questions in the chat window, and at the end, I'll run through them and ask our presenters to answer your questions. If we don't have time to reach all your questions, we'll reply to you by email with answers. And we'll also be providing a link to this video after the webinar as well. So before we get started, just a little bit about Koch Modular. We are basically a joint venture company with Koch. We've been in business for close to about 40 years now, and we touch pretty much every market and industry that has chemicals related to it. So more than likely, we function in your business sector. Services really divided into 3 different sections. We're primarily process engineers. The company is made up predominantly of process engineers and have various expertise in difficult separations, whether it be distillation, liquid-to-liquid extraction, gas absorption, steam stripping, and also we do some heat exchanger design. We also backed up with a pilot plant located here in Houston. Don and Brendan will be sharing some of those details about that in their presentation. And then ultimately, all our projects are delivered modularly. We do not stick build any of our projects. And the benefits of modular construction is that we're able to eliminate probably close to 30% of field work. Everything is done at the fab shop, factory acceptance tested before it goes out into the field. And we're also able to lower construction costs compared to traditional stick build by 25 to 30%, depending on location and other factors. Some of the other benefits are we're able to provide lump sum pricing, shorter time to market, permitting and construction is simplified, it's much safer, and provides a single source responsibility. That's about Koch Modular. Want to introduce the team before we get started. So on the call will be Don Glatz, Manager of Extraction Technology. Don has been with the company for over 30 years, extensive experience in liquid-to-liquid extraction, has written various articles, presented many presentations and conferences on the topic. He holds a BS in chemical engineering from Rensselaer Polytechnical Institute and an MBA from Fairleigh Dickinson. And then joining Don is Brendan Cross, Principal Extraction Engineer. Been with Koch Modular now for 15 years, many of those years working side by side. Don, learning everything there is to know about extraction technology. Brendan has a BS from Columbia University in chemical engineer. So with that, I will hand it over to Don.
Okay. Well, good morning, everyone. Both Brendan and I typically work in New Jersey, but right now I am in our pilot plant in Houston, Texas, because we are running a extraction test today. So that's what we are talking about in this seminar. So this first slide we have up here then does show where you would want to apply liquid-liquid extraction. And you can see there's about 7 different areas we've identified here. However, probably most of the work we do in extraction are in the first 3 that you see here. So the first one, certainly, if you have an aqueous stream and you have higher boiling organics in that stream, higher boiling than water, it's not economical to boil water away, from those chemicals, because it takes a lot of energy to boil water. So oftentimes, if you can find a solvent that will selectively extract those components, that's going to be a much more feasible and economic process. And the second one is kind of the same, where you have non-volatile components, usually in an aqueous stream, and like metals extraction and things like that would be done by liquid-liquid extraction. The third one, oftentimes water is the solvent in extraction. So if you have something in an organic stream, maybe a salt or maybe an immiscible catalyst or something that you can extract with water, then you would use water for a countercurrent liquid-liquid extraction process. And then you can see there's some others there that I'm not going to get into in any real detail at this time. So What industries use liquid extraction? You can see of just about everything in the CPI industry would be using liquid extraction. Certainly a lot of work is done in the chemical industry, things like acetic acid extraction and, removal of polar compounds from, aqueous streams and recovery of oftentimes just valuable products that companies are making. In mining and minerals, again, I mentioned this before, there's different metals that you extract by liquid extraction. We've been doing a lot of work with lithium lately. However, in the past, we've done copper, cobalt, nickel, those types of extraction processes. In polymer processing, oftentimes you have polymer solutions where you want to extract components to purify those polymers, or like in caprolactam, that's a precursor to making nylon. And if you look at the caprolactam process, it has a number of extraction columns that are used to, purify and then recover that caprolactam. And then in the last, 15 years or so, biochemicals have become a huge business for not only us, but a lot of people. So people try to make chemicals by natural processes, maybe a fermentation process, an algae process. And oftentimes those broths then have high boiling chemicals in them that you're trying to recover. And again, liquid extraction is a good tool to use in those processes. Certainly, effluent treatment has always been a good area for liquid extraction, because if you got wastewater that has chemicals in it that you got to remove, and they're higher boiling than water, then again, the way to do that oftentimes is by liquid extraction. Okay. So this shows what extraction is in its basic form and gives you an idea of some of the terminology we like to use in liquid extraction. You have a feed that has something in it, in this case, component C, you want to remove from that feed. So you want to bring that feed in contact with an immiscible solvent. You want to mix those two phases together, and you want to affect a mass transfer of that solute from one liquid phase to the other liquid phase. So again, if this feed is an aqueous phase, that solvent could be anything like ethyl acetate, chloroform, benzene, toluene, lots of immiscible solvents, but you want to pick one that will selectively extract that component C. So after you've reached steady state, you then separate the two phases. And when you separate it, you get what we call a raffinate phase. That's the feed that's given up the solute. And we have an extract phase. That's the solvent that has picked up the solute that you want to recover. So assuming you mix long enough to reach equilibrium or steady state, this would be one theoretical stage of extraction. And around that, we can make some calculations. Certainly, the fraction unextracted is simply how much does not extract in that one stage at the given solvent to feed ratio that you're using. The distribution coefficient, this is something you want to calculate for almost any liquid extraction process. And that's defined as the concentration of the solute in the extract phase divided by the concentration in the raffinate phase. Here we're showing it to be pretty high at about 8. So what you really want to do is find a solvent with as high a distribution coefficient for this material that you want to remove, and then of course low as possible for things you don't want to remove from that feed. And then there's the extraction factor. That's this distribution coefficient, M, times the solvent to feed ratio. And in this particular case, we're showing it to be 4. So in our company, we have a rule of thumb. We like to target a minimum extraction factor of 1.3. And I will show you in another slide, where exactly that comes from. So obviously, when you do a batch process where you mix and decant, what I just showed, 80% extraction is not going to be good enough for that kind of a process. So what you then have to do is, after your first mix and decant, you then take the raffinate, you add fresh solvent to it, you mix it up again, decant it again, and do that as many times as necessary to get from the feed concentration to the raffinate concentration that you're looking for. This is called cross-flow extraction because you're cross-flowing with the solvent each time and using fresh solvent in each of your mix and decant steps. However, usually a much more economical process then is to use a true countercurrent process. Here you see the same 4 stages, but now you bring the solvent into the 4th stage, and then the extract from the 4th stage becomes the solvent in the 3rd stage, and so on in a true countercurrent fashion. And if you run through the calculations of with the solvent to feed ratio the same and the number of stages being pretty much the same, using cross flow or countercurrent as we're showing here, you can get to pretty close to the same raffinate concentration. Not exactly the same, obviously, but pretty close. But what you've done here is you significantly reduce the solvent usage. In this example, we're only using 25% as much solvent to do this extraction process. And that's where the economics of your process start to come into play, because that solvent typically has to be recovered downstream and recycled back to the extraction process. And oftentimes in a chemical plant, that's recovered by a distillation. And that distillation step then is where the bulk of your energy cost is. So usually the best process, the most economical process, is to minimize your solvent usage, and then you're going to have a more economical extraction process. And the idea then of an extraction column is to create theoretical stages as the two phases flow countercurrently. In this particular example we're showing here, the feed is the heavy phase. So say that is an aqueous stream, and so it's heavy. And solvent, say that's toluene, which has a lower density than water. So that would come in at the opposite end of the column, at the bottom of the column. And then these two phases will flow countercurrently inside that column, and you'll do something inside this column to create theoretical stages, which we'll talk about in a couple of minutes. In an extraction process, you have two phases in a column. You have a continuous phase and a dispersed phase. In this example, the feed comes in and it fills the column. So that's the continuous phase. The solvent comes in and it's broken up into droplets then, which flow up through the continuous phase and eventually form a primary interface above the feed location. So that's the dispersed phase. And then the extract coming out the top and the raffinate going out the bottom of the column. One of the really nice things about liquid-liquid extraction is that it's very, very easy to generate your liquid-liquid equilibrium data for your process. We like to use what you show here in the picture and what you see in the example over here, a round bottom reaction type flask with a jacket so that we can control the temperature, and a bottoms takeoff valve. So what you want to do is you put your feed in here, you want to put your solvent in here at a specific ratio, you want to mix it real good. We find that for most applications, two minutes of fairly high speed agitation is enough to reach steady state or equilibrium. So then you turn your agitator off and you allow the phases to separate. Typically, if you need to go more than 2 minutes, it's because you probably have a very viscous material as one of the phases or both of the phases. And in that case, you might have to mix for more than 2 minutes. So after you've separated the two phases, you draw off the heavy phase first and then the light phase next. You take a sample, you give it to your analytical chemist, and they analyze for the solute in each phase, and you have a distribution coefficient at that concentration. You then put the raffinate back in, add fresh solvent to it, mix it up again, decant it again. And we like to do that at least 4 to 6 times to get from the feed concentration that you have down to the raffinate concentration that you're looking for, because the distribution coefficient can change with concentration. And so it's important to measure it throughout the whole concentration range that you're looking for in your process. So this method is great because you can generate your distribution coefficients, you can screen the solvents, but the other thing you do here is to perform a qualitative observation inside this mixed decant vessel. We want to know things like, once you turn the agitator off, how quickly do the phases separate? Is it seconds or does it take many minutes? What happens at the interface? Do you get a solids forming at the interface, which we would call a rag layer? Or sometimes you have the two phases just don't want to separate real well at the interface, and you get what we call kind of an emulsion band that may take quite some time to separate. And then you also want to see if there's a tendency to have some entrainment of one phase in the other phase. All these things are important for us along with the raw equilibrium data, because that helps us as we look downstream, down in your process development, what type of column you want to test for your application. So when you're doing these mix and decants, what you're developing is the equilibrium curve, which is the blue line shown over here on the right. Y being the concentration of the solute in the feed and the solvent or the extract phase, and X being the concentration in the feed or the raffinate phase. So your first mix and decant, you'll be this upper point on this blue equilibrium curve. And then every time you mix and decant, you'll be a lower and lower point on this equilibrium curve. Now, if your distribution coefficient, which I'm shown to be M, is constant, you'll get a straight line as we show here. But that's not always the case. Like I said, a lot of times the distribution coefficient can change with concentration. So once you have your equilibrium curve, now you run an extraction column, you develop your operating line, you can then step off the number of theoretical stages that are required. So when you look at this operating line, this red operating line, this upper right-hand portion of the operating line is where the feed comes in and the extract goes out. So in this case, it's the top of the extraction column. The other end of the operating line, the lower left, that's where the solvent comes in and the raffinate goes out. So now you draw your operating line and you can step off your number of theoretical stages using the typical stepping method that you use for something like a McCabe-Thiele calculation. Now, this is some data we generated a few years ago. This was a extraction of a dicarboxylic acid that was created by a fermentation broth. You see the red line is the equilibrium curve, and now you can see this was a real curve. That when we were at a somewhat higher concentration, you had a higher distribution coefficient, but then as you got down into the low concentration range, it got less and less. So, this, if we wanted to look, once we had that equilibrium curve, if we wanted to calculate how to get 98% extraction of our material at a solvent to feed ratio of 1, we would then, by material balance, determine what our operating line would look like. So the upper part here is where the feed comes in. You know what that is. If 98% extracts, you can calculate what the extract concentration needs to be. The other end, if you want 2% of your solute left, you know what your raffinate concentration needs to be. And of course, you know your solvent coming in. So you draw your operating line, and you can see you have to step off 6 theoretical stages at a solvent to feed ratio of 1 to get 98% extraction. You can also calculate your distribution your number of theoretical stages using a Kremser equation, and the equation is shown in this white box here. Now, the thing about the Kremser equation is the distribution coefficient is a constant in this, so it really only works if your distribution coefficient does not change too much, for your application. So then how you can also calculate the number of theoretical stages versus solvent to feed ratio, and that gives you a good idea of where you might want to operate your column. And you can stick this into an Excel spreadsheet and very quickly make those calculations. You can also use a Kremser curve. And now these curves you see on this diagram here, these are curves of extraction factor, which I mentioned before was the distribution coefficient times the solvent to feed ratio. So the y-axis here is your fraction unextracted. The x-axis is your number of theoretical stages. So a simple example, if you were extracting phenol from wastewater using toluene as your solvent, which we've done, that has a very constant distribution coefficient, about 2 over the whole concentration range. So if you were using a solvent to feed ratio of 1 part toluene to 1 part feed, and you wanted 99% extraction, so at a 1-to-1 ratio with a 2 distribution coefficient, your extraction factor is going to be 2. So this curve right here is the 2 curve. And if you want 99% extraction, 1% unextracted, you come over to that curve and it says you're going to need slightly more than 5 theoretical stages for your process. So using either this curve or the equation itself is something you would typically use early on in an extraction process. After you've generated your equilibrium data in the laboratory, you now start to look at solvent to feed ratio, versus the number of theoretical stages you're going to need for your process. Okay, so now I'm going to talk a little bit about what an extraction process would typically look like, at least in the chemical industry. We see this quite often. you have three columns: the extraction column, a stripping column, and a distillation column. So in this example, if we have acetic acid that we want to extract, typical solvents for acetic acid are ethyl acetate and MTBE. You can see their heat of vaporization is quite low, much lower than water, and that's why these processes are very economical. So you would bring the aqueous feed in the top, the solvent in the bottom, it would flow up, it would extract the acetic acid, and then that extract would go over to the distillation column where you would distill the solvent overhead, and you would recover the acetic acid as a bottoms product in this particular case. If there's other, say, heavy components in there, you might need another column to further purify that. But this is why I said before, the most economical process is to use as low a solvent to feed ratio as possible, so that you're not putting too much energy into this distillation step, because probably 90+% of the energy cost for this process is going to be in that distillation column. Coming out the bottom of the extractor, you do have a certain solubility of the solvent in the aqueous phase, and you got to recover that as well, plus purify your wastewater. So in that case, you would put a simple stripping column in. This column typically does not take very much energy, but you can recover better than 99.9% of your solvent in a stripping column like this. And you can see both of these are going to a separator, and then you're recycling your solvent back to the extraction column. There's another type of extraction process which is called fractional liquid extraction, and that's where you have two solvents and one feed. So in this case, we're showing a feed that's a mixed polymer stream. This was actually a 50-50 mixed polymer stream that we want to bring in somewhere in the middle of an extraction column setup. And then you have one solvent, in this case methanol, which is would be brought in at the top because it's actually a little heavier than the hexane. So that would extract, in this case, the more polar components from that polymer solution. And then at the other end, you're bringing hexane in, and that, being a straight chain, would preferentially extract the non-polar material, the straight, the more, I guess, the non-polar components of that feed. So I'm showing this in two columns here because when we actually tested this in our pilot plant, we needed a lot of theoretical stages, and so it was easier to set up two columns. But if you could kind of think of this as the bottom of this column being attached to the top of that second column, that's how this would be operated. And in this case, you can see you did not need a lot of stages for the methanol extraction, but you definitely needed a lot of stages for the hexane extraction. And this is something we optimized in our pilot plant by trying a whole slew of different, stages above and below and different solvent to feed ratios. But when we did, eventually we got 99% of one polymer coming out with the hexane phase, and 99% of the other polymer coming out with the methanol phase. Okay, I switch gears now, and I'm going to talk a little bit about different types of extraction equipment. This is an overall view of what you would find as equipment that can be used for liquid extraction. Mixer settlers can be either batch mixer settlers, which is more of a mixed decant, or a continuous mixer settler, which kind of acts kind of like a CSTR, where you're continuously feeding both phases, continuously overflowing and separating. There's centrifugal extractors, which use high speed to force the phases against each other. And then, of course, there's a lot of different types of column contactors. There's static columns like pack columns or trade towers typically. And then there's a number of different agitated columns, including pulse columns, columns with rotating internals, and columns with reciprocating internals. Our company primarily deals with pack columns, rotating internals, and reciprocating internals. So due to the time restraints, we're just going to kind of talk about those types of columns here. A pack column, you can use either random packing or structured packing. In my experience, there's no real difference in efficiency between random packing and structured packing for liquid extraction. I know there is a big difference in distillation, but that doesn't carry over to liquid extraction. The big difference you can see is the capacity. Structured packing has a much higher capacity than random packing. Now those capacity numbers, gallons per hour per foot square or meters cubed per meter square hour, that's you take the feed rate and add it to the solvent rate and divide by the cross-sectional area of the extraction column, and that's what gives you that number. It's kind of an average over the whole whole length of that column. With a packed column, you are limited as to which phase you can be a continuous and which phase to be dispersed, and that's mostly based on the material construction. Brendan's going to talk a little bit about that, but basically you want the dispersed phase to not wet the internals. You want the continuous phase to wet the internals. If the dispersed phase wets the internals, the droplets are going to coalesce, you're going to form films, and then you're going to lose surface area. These columns can be affected by changes in wetting characteristics, and that's something you have to be concerned about. And as the column diameter goes up, the efficiency will go down significantly because you get a lot more back mixing in these types of columns. So they're not good also for fouling services. Obviously, if something plates out on those internals, it could change the wetting properties. And we would typically see this when you have lower interfacial tension and not too many theoretical stages required, say up to maybe 5. Then we talk about 2 types of agitated columns. We have the miscible column, which you can see a kind of a diagram of here. This is a series of turbine type impellers. It has inner baffles and outer baffles. So this is the most efficient column based on data published in the literature. And the reason it's so efficient is because you have a very good mixing impeller with turbine type, and then all this baffling which directs the flow and helps minimize back mixing. So it's got the highest efficiency of any column in the marketplace. That's based on data that's been published. Typically 5 to 6 of these agitated stages will give you 1 theoretical stage. It also has a really good turn down to 25% at design. So it's really best suited when, say, you got a high interfacial tension, high density difference system. You need a lot of agitation to break the phases up. This column is going to be the best choice for that type of a system. We don't recommend it for systems that foul or emulsify, and that's because I'll tell you about the car column in a minute. Just a couple of pictures of a miscible column. What you're seeing here is a 6.5 foot diameter miscible column on the left. You can see the inner baffles with the turbine impeller between the stages. And then on the right, and on this one here, you would actually weld the outer baffles to the inside wall of the vessel. On the right, you see a complete cartridge. What you're looking at there are the outer baffles, and then inside each of these sections would be what you see here, inner baffles with a turbine impeller. This is a smaller diameter, 30-inch diameter. Now you can see this really well with the outer baffles with a Teflon edge to seal the wall, the inner baffles, and the turbine impeller in there as well. The car column is different. Instead of having rotating internals, it has a plate stack that reciprocates up and down. And the key to the car column now is that you have uniform shear mixing across the whole cross section of the column. And we have found that this is the type of mixing that works best for low interfacial tension, low density difference systems, systems that tend to emulsify very easily. This is the type of column that works best for those types of systems. And the fermentation broths, algae broths, those kind of things tend to work best here. It also has the good turn down, and it also can handle solids. We've put up to a 40% slurry through a car column, and that's because this whole plate stack is moving. Well, I'll show you what that looks like in a second. And that's why the solids have nowhere to build up inside the column. So this is a plate stack you're looking at a 3-foot diameter car column. If you look on the left here, you can see a perf plate, and that has 55 to 60% open area. That's what gives it high capacity. They're typically spaced 2 inches apart or 50 millimeters apart. And then in addition to the perf plates, we have these baffle plates, which you see with the white edge on. Those are donut-shaped plates. And this Teflon edge is the highest diameter anywhere throughout that plate stack. So if there's ever going to be wall contact, it's going to be that Teflon to the wall and not, metal to wall. And then you got what we call spider plates. These are heavy-duty plates that you see. In this case, one on each end of the column, one in the middle, so that when you tie it together with these tie rods, that's what makes this a very rigid structure. This is another plate stack we recently installed into a column. This, in fact, was the largest diameter plate stack we've ever built, and this was for an 84-inch diameter column. And if you look closely, you can see we varied the plate spacing throughout that, and that's because the hydraulic behavior was changing throughout that column. So when we tested this, we learned how to, space the plates correctly to get the best kind of efficiency out of that column. This is data published in the literature. I don't want to go through this too deeply. This is efficiency versus capacity. We generated these curves. A German engineer named Stickelmeyer created the shaded regions. But this is why we say the miscible column has the highest efficiency based on data published in the literature, because it is, the grazer, by the way, is not even a column. It's more of a horizontal unit. But the miscible column has the highest efficiency. And then the car column actually runs at very high capacity, as you can see here. Okay. So before I turn this over to Brendan to talk about, pilot testing and things, I mentioned before that, we can, once you generate liquid-liquid equilibrium data, we can then use that data to actually get you an idea of what the commercial column is going to be looking like. So if you've done some lab work, you've developed your mixing and settling behavior, you've got the equilibrium data, you give us the feed concentration and the raffinate that you're looking for and the design capacity, we can, first of all, select what we think will be the optimal column. We can make a preliminary design based on our experience, diameter and height, and get you a budget cost for that extraction column. A lot of times in that phase of the project, you need this information in order to know whether you got a viable process. And then we're going to give you a proposal for pilot testing. And like I said, Brendan will be talking about that. All yours, Brendan.
Thanks, Don. And thanks everyone for joining today. So I'm going to be talking about pilot testing mostly in my portion of today's webinar. And really the reason you want to perform a pilot test before you build any type of commercial scale extraction column is because there's a lot of things that can happen at the liquid-liquid interface that are really difficult to predict or anticipate in advance. So you wouldn't want to just design an extraction column using simulation software like Aspen, or designing one in Excel, or using hand calculations, things like that, because of all these different things that can happen within a column. And this is what you see when you run a pilot test. Some of the things that can be really problematic in an extraction column during pilot testing that you can't predict in advance, or if the liquid-liquid system shows a strong tendency to emulsify, that would be a good time to use a car column. What the effect of impurities in the feed or solvent can have on the extraction process, and also what the impact of solids can have on the extraction process and operating that extraction process. Also things like the impact of coalescing on the internals and the wetting characteristics of both liquids on the internals. Those can have a huge impact on just running the extraction process itself. So you always want to run a pilot test, and that's the best way forward. Run a pilot test, and then based upon the results of the pilot test, use the known equations and correlations for the extraction technology that was tested to scale up to the commercial scale design. So this is something kind of Don touched on earlier, which phase is continuous and which phase is dispersed. Well, the first thing here is that you make a selection on which you'd like to be dispersed and which you'd like to be continuous in a countercurrent extraction column. So that selection's made, and that's something I'll touch on the next slide, how you actually make that selection. But then really it's just a function of the relative specific gravities of the two liquids that you're running in your column. So you can see in this slide, there's 4 examples here, depending upon which phase was selected as continuous and the relative gravities of both liquids. You can see on the upper right-hand side of the slide, there is the solvent's a continuous phase. It's lighter than the feed, so it's flowing up through the column, leaving the top as extract. Here, the feed is dispersed. It's being broken up inside the column, flowing down the column, leaving the bottom as raffinate, and of course those droplets coalesce on the bottom of the column, leading to a controlled interface at the bottom. But how do you pick which is which. You have to make that selection ahead of time when you're coming up with a preliminary column design or before you run a pilot test. So what we like to do is we have 4 rules of thumb that we like to look at before we come up with a preliminary commercial scale column design or we run a pilot test. The first of those is just looking at the relative volumetric flow rates of the feed and solvent going into the column. So for a static column, like a packed column that Don discussed earlier, what you want to do there is you want to disperse the higher flowing volumetric phase. And that's because you're kind of counting on that higher velocity and momentum associated with that phase to be broken up by those fixed internals like structured packing. For an agitated column, we take the opposite approach. We want to disperse the lower flowing phase because we have those rotating internals like a miscible or those reciprocating internals like a car. Those act to break up the dispersed phase into droplets. And if it's a lower flowing phase, it's going to have more resonance time inside the extraction column, and having more resonance time inside the extraction column of that dispersed phase usually leads to better extraction and better efficiency. Something else we look at is viscosity. And the key takeaway here is the more viscous phase, generally speaking, you want to have that as the dispersed phase. You can imagine if you were processing a process that contained a polymer solution and it was really viscous and you had that as a continuous phase, it's going to be really difficult to run that column because there's going to be so much drag put on those droplets as they rise or fall down the column. So you want to have the more viscous phase be dispersed if you can. Something else we look at is the impact of surface wetting. So really the takeaway here is you want to have the continuous phase be the one that preferentially wets those internals. So for example, if you had a car column and you had an aqueous organic system and it had 3/16 stainless steel internals, you'd want that aqueous phase to be continuous and the organic phase to be dispersed. So those organic droplets would bounce off the internals and you wouldn't lose interfacial area. As soon as you have droplets coalescing on the internals, you lose a lot of interfacial area. And of course, that's really going to impact the mass transfer that takes place inside an extraction column. The last thing we look at is something called the Marangoni effect. And essentially, this is the impact of mass transfer on interfacial tension. But what you want to do here is you want to have the mass transfer direction go from the continuous feed to the dispersed solvent if you can. That can have a huge impact on extraction efficiency inside an extraction column. So when we're reviewing an application, either for a preliminary column design or if we're designing a pilot test, what we like to do is just put these 4 rules of thumb on the table, look at all of them for the application that we're investigating, and then make a prudent decision based upon them. And then something else I always like to say is that I feel like 85–90% of the time we get phase selection right when we're running a pilot test. But the advantage of running a pilot test is that you can always swap the phase selection if you're not getting the extraction efficiency that you're looking for. So another advantage of pilot testing right there. Also in pilot testing, we see interesting things that happen at the controlled interface in the top or bottom of an extraction column. 2 of those things that we commonly see are shown on this slide. The first is something called a rag layer. Rag layer is essentially where you have solids build up at the interface. And then there's also something called an emulsion band. And this is essentially where your dispersion is coalescing at the interface, at that controlled interface, but it's taking time to come together and form a uniform liquid phase. So we see both these things when we're running pilot tests, and there's a few ways you can combat them. Something you can simply do to combat an emulsion band is just by reversing the phases, because now your dispersed phase that was taking time to coalesce at the interface is now the opposite. So that may just take care of it altogether. Also, for an emulsion band, you can slow down the capacity, which really means just reduce the feed and solvent rates to the column, or you can reduce the agitation speed. As you dial back the agitation speed, the droplets that are going to be within the column are larger, so it'll take less time for them to coalesce and come together at the interface. For a rag layer, what you can do is you can put nozzles around where that interface is in a commercial column and then pump liquid from the interface through an external filter. So then you just have clean filtrate going back to the column. So whenever we scale up to a commercial scale column, even if we don't see a rag layer forming at that controlled interface, we always put nozzles around where it'll be in the commercial scale column, just so our customers have that flexibility. If a rag layer does form down the road, they can install the appropriate pieces of equipment to take care of it continuously. Something else we see in pilot testing is something called entrainment. And entrainment is essentially just where you have discrete droplets going out the wrong end of the column. So you can see in the first picture on this slide, here again, we have dispersed feed coming in, flowing down the column, leaving as raffinate, but we have some droplets going out with our extract stream, which we don't want. So there's a few ways to take care of this in an extraction column. The first way is just having an expanded end on the end of the column where you're seeing entrainment. By doing that, you lower the continuous phase velocity in that section, and oftentimes that'll take care of entrainment right there. You can also put a coalescing element in that end of the column where you're seeing entrainment. Those discrete droplets will hit the element, coalesce, come together and form larger droplets, which will allow them to go out the right end of the column. That's something we often do when we're running a pilot test in our pilot plant in Houston to take care of entrainment. Then the last option is you could actually have an external vessel with a coalescing element in it to basically serve the same purpose. The benefit here is that if for whatever reason you needed to perform some maintenance on that external vessel, like clean that coalescing element, you could temporarily bypass it, and that would allow you to continue to run your extraction column. Something else we always look to see in when we run a pilot test is flooding. And this is essentially where your dispersed phase gets held up within the column and forms another interface inside. So, of course, commercially, this is something you want to avoid. And the way it happens is either by having too much flow into the extraction column or just too much agitation. So in the top part of this slide, that's where we have too much continuous phase flow into the extraction column. That just continues to increase the continuous phase velocity, and eventually it gets to the point where those droplets are held up inside the column. Another way this can happen is just by having too much agitation speed. So there you just make the droplets smaller and smaller, and although your continuous phase velocity is the same, eventually those droplets get so small that they get held up within the column. Whenever we run a pilot test, we like to fly in the flood point for a few different reasons. First is just to know at what conditions the extraction column will flood. That's just good information to have. The second thing is that the extraction column typically operates at its highest efficiency as you approach the flood point. So it's always good to know what that flood point is and to approach it so you can get the most efficient extraction during your pilot test. The last thing is that we also want to know how difficult it is to get an extraction process out of a flooding scenario. And that could just be by reducing the agitation speed, reducing the rates, the feed and solvent rates to the column. But at times we've seen it so severe where we have to cut off the agitation entirely or cut off the feed and solvent rates to the column entirely as well. So we just want to know how hard it is to get out of that flooding scenario. So in Houston, we have a pilot plant that's essentially dedicated to testing extraction processes. We can test car columns there, miscible columns there. We've also tested packed columns and RDC columns there as well, but we primarily test car and miscible columns. We also have the capability to test distillation as well, and often that ties into an extraction test for downstream solvent recovery or something like raffinate stripping, like that flow diagram Don showed earlier. We have the typical analytical capabilities in-house that you would associate with a site that does process development like GC, HPLC, and IC. And then, of course, we also have good relationships with labs like SGS in Houston that we work with for fast turnaround analysis on something that we can't do in-house. Tom Lightfoot, who's our pilot plant manager, and myself, we wrote an article for CEP magazine back in 2018. And this article does a really good job of giving our philosophy and methodology when it comes to extraction pilot testing. So in addition to everyone kind of taking part in this webinar today, if you have some time, this article is also worth a read as well, in my opinion, because it goes into more detail and provides more case studies than we'll provide today. So the next series of slides will provide some details on a specific pilot test that we went through a few years ago, where we were looking to recover carboxylic acids from a fermentation broth. So the goal here was to recover 95% of the acids from this 5% acid aqueous stream. And we also want to reduce the amount of solvent that was required as well. Ethyl acetate was selected by the solvent, or by our customer, was the selected solvent for this process, but they noticed that it emulsified very easily, even when they just conducted shake tests. So they also tried running this in an RDC column, which is a rotating disc contactor column. And that column, similar to a miscible, since it's rotating, it's not great for processes that tend to emulsify. And that's what our customer found, is that it was very difficult to run this column because it was so prone to emulsification. Not only that, they weren't able to recover the amount of acid that they were hoping. Less than 90% is what they achieved. And they also had to use a relatively high solvent to feed ratio of 2. So since this process had such a high tendency to emulsify, we knew a car column was required. And this is what our setup looked like. This is a very typical pilot setup for us when we're running an extraction test. You can see the car columns in the middle there. Here, the ethyl acetate solvent was going in the bottom. It was dispersed, flowing up, coalescing at the top. That's why the interface is up at the top there. The feed was continuous here. So our mass transfer direction was from the continuous feed to the dispersed solvent. So we were taking advantage of the Marangoni effect for this process. One thing I also do want to mention, this was a 1-inch diameter glass shell car column. Virtually all of the pilot testing that we do is in glass shell columns, whether it's a 1-inch diameter car or a 3-inch diameter miscible. There's huge benefits to that. Really, it just allows you to see everything that's taking place within the column. And especially when you're looking for something like you're trying to find a flood point, that's really, really beneficial. So you can learn a lot just by seeing everything when you're running an extraction pilot test. And that can really help you out with scale up as well. So this slide shows how we optimized this extraction process when we were running our test in Houston. There's a series of runs here. And you can see in runs 1 through 3, we had a plate stack height of about 12 feet, running at a fixed capacity with a solvent to feed ratio of 1.7. And we pushed the agitation speed here until we found the flood point. And this system only flooded at an agitation speed of 50 strokes a minute, which is pretty low for a car column. So that shows how sensitive to emulsification this system was. We then reduced the plate stack height down to 8 feet, but we weren't able to make spec here. We then tried kind of picking a middle ground of the plate stack height of 10 feet between 12 and 8. We made spec there, but we started looking at the solvent to feed ratio, and we really wanted to pull that down if we could. So we went back to 12 feet, reduced the solvent to feed ratio down to 1.5, and you can see in run 7, here we were able to easily make spec, and then run 8 as well. We also made spec at a slightly lower capacity. We then made what proved to be the key parameter change for this pilot test, and that was just by increasing the temperature to a moderate elevated temperature of 45 degrees Celsius. And you can see in runs 10 and 11, we had excellent recovery at those conditions. So the next thing we did is we kind of looked over all the runs, and we used runs 7 and 11 to scale up to the commercial scale extraction column design. And the reason we also included run 7 was we wanted our customer to have the flexibility to run at a lower temperature if they needed to. say you're running in the winter and you weren't getting as much heat conservation in the process as you expected, just having that capability would be worthwhile. So that's why we included run 7 in addition to run 11 for scale up. And this is what the basically what the commercial column turned out to be. So it had a 22-inch diameter, and the reason that was 22 inches is basically you have the same capacity that you tested. It's a 1-to-1 scale up for a car column. So since we tested at 650 gallons per hour per foot squared, that's what the scale. That's what we used for the scale up design, and that worked out to be 22 inches since we knew the solvent to feed ratio and the commercial scale feed rate. There's equations that we use to determine the height of a car column, and also the operating speed, which kind of sets the standard operating speed for the drive assembly. But of course, that's something you can fine tune in the field later on. But those equations are basically relative to the diameter that was tested, the diameter of the commercial column, and then the height that was tested and the speed that was tested. So in a nutshell, that's how we scale up a car column. And in this slide, there's a picture on the right that shows what the car column ended up being in terms of size. It had 38 feet of plate stack height. Its overall height was 50.5 feet. Like I said before, it had 22 inches diameter in the agitated section. On car columns, we do put expanded ends on either side just to minimize any potential entrainment. So those are 44 inches in size. And this was part of a complete modular system that also had solvent recovery and raffinate stripping, much like the flow diagram that Don showed earlier. So this is a complete modular system here. In the module on the left, you can see the large car column there. In the module on the right, the large column there is the solvent recovery column. The smaller column in the front is our raffinate stripping column. And you can see this came with all the required peripheral instrumentation and equipment as well. And on the bottom floor of the left module, we have a complete control system down there as well. So this is a complete system that was provided to our customer. So with that, we've tested hundreds of processes in Houston. We've provided hundreds of pilot columns, and then worldwide, we've also provided hundreds of miscible and car columns on the commercial scale.
Great, thanks, Brendan. Thanks, Don, for presenting this material to our attendees. We did have a few questions, and we have a few minutes to answer them. I will read some off, and then you guys can take turns answering those questions. So the first one came in. It says, on average, how much time does a single run take to complete? Achieve steady state, get your data, and move on to the next run.
I'll take that one, Don. So it really depends upon the feed and solvent rates to the column and the volume of the column itself. So typically, to reach steady state, you need 5 turnovers. So that's the turnover is defined as basically the residence time of the column based upon the volumetric feed and solvent rates. So it is kind of process dependent, but generally speaking, I want to say it's something like 90 minutes probably for most extraction processes that we test will be 5 turnovers, and then 3 turnovers afterwards. After you make a change, you only need to have 3 turnovers to sample again. That's probably something like an hour and 15 minutes on average for most extraction processes that we test with typical feed and solvent rates into a 1-inch car column or a 3-inch miscible column.
Yeah, I'll just piggyback on that because we're running a test right now here in the pilot plant, like I said, and we're exactly what Brendan just said. We're getting that kind of time frame for the runs, and we're getting maybe 6 runs in an 8-hour day. So you can do a lot of runs in a single day in an extraction column.
Great, thank you. Another question is, are there any technological advantages of vertical extractors over horizontal ones?
So
there's only, I'll answer that, Brent. There's only one type of horizontal one that I've ever seen commercially. It's the grazer one we showed in that slide, and it is very, very low capacity, and it only gets a couple of theoretical stages. It's called a rainy bucket. You'd have to look that up. So the real advantage of a vertical column is you can get much higher throughput and you can get a lot more efficiency. Like I said, the horizontal one gets about 2 theoretical stages, but we can get 10 or even 15 or more theoretical stages in a vertical extraction column.
I was going to ask Don if you'd ever
Okay.
seen a raining bucket contactor in the field, because I didn't know that. So that
I have.
if you've only seen one,
I have
that says
seen
a lot.
Well, it was one plant that had 2 of them, but they were very, very old. So yeah, and they only got like 2 theoretical stages.
The only comment I'd made there, that the other ones that maybe could be considered horizontal are mixer settlers and centrifugal contactors. Centrifugal contactors, to get more stages, you're just going to have to buy more. And those are high-speed, expensive devices. So I would say cost-wise, they're going to be much more expensive to run and probably to buy for the same capacity as a countercurrent agitated column. And then mixer settlers, you have to control an interface downstream each mixer. So whether that's like a large rectangular design like you see in the mining industry, or if you're using a series of tanks and with mixers and settlers, it's going to be more, in my opinion, troublesome to operate, because you have to control each of those liquid-liquid interfaces. And if there's any issues like emulsion bands or rag layers, you're going to have that at each interface within a mixer settler system.
Great, thank you. One last question is, Koch's liquid extraction technology literature indicates that miscible columns can have up to 10 stages per meter of tower height. Are these theoretical equilibrium stages, or does a stage efficiency need to be applied? If so, what is the stage efficiency typically?
Well, again, when I was talking about the miscible column, I said 5 to 6 agitated stages per theoretical stage. As the diameter goes up, the height goes up of each of those agitated stages. The number he just mentioned in that question, I think, is for the 3-inch column, where you can get, maybe 10 theoretical stages, 12 theoretical stages in a meter of height. But in a, say, we just built 120-inch diameter column, the HETP there is probably closer to 3 feet, per stage. So it really depends on the diameter of the column, what the height per theoretical stage will actually be.
And just to piggyback on that a little bit, this really shows the value of pilot testing. That's where you really determine whether it's a miscible column or a Koch column. That's where you really nail down the efficiency, because we have estimates that we use in advance when we design a pilot test. Like Don was saying, 5 to 6 agitated stages per theoretical stage for a miscible, or in a 1-inch car, something like 1 to 3 feet of height, of plate stack height per theoretical stage. But that's something you ultimately determine through pilot testing.
Great, thank you. We have 2 minutes left, so with those 2 minutes, I'll mention that, Don and Brendan's email address is at the bottom of this slide. Feel free to reach out to them if you do have any other questions. As I mentioned, we'll be emailing you the link to this presentation, so you'll be able to access this later once we get it published on our website. And then also keep an eye out for emails related to our upcoming webinars. On November 17th, we're going to be doing one related to concept to commercialization, basically how to navigate process development through scale up. And then on December 8th, we're going to be discussing designing complex distillation systems for difficult separation, purification, and recovery of valuable chemicals. We'll be covering a bunch of different distillation techniques there. So again, thank you all for attending, and have a great rest of the day. Take care.
Thanks, everyone. Bye.